Have you heard of the determinant and really want to understand what it is? I'm going to break it down in this video. Or maybe just stay for the cool pictures. I'm going to draw everything with areas in 2 dimensions, but this would extend in 3 dimensions with volume as well. A matrix is really transforming vectors into other vectors. For instance, that orange vector gets stretched and pulled down, whereas that blue vector gets stretched and pulled the other way. In general, these can be pretty complicated. A pretty natural question we might ask is whether we can undo this process. Could I find some vector over on the left that's going to go to that one I drew over there? We might solve equations that look like this, and that's where linear algebra usually starts. The answer is in general yes, unless we've collapsed something, and I want to show you what I mean. Here's a matrix where every single vector on the left gets sent somewhere on this line. Now that's kind of cool, but that means if I tried to find some vector that goes to that one, it's going to be impossible. So I can't undo this operation. And there are also other problems, like the pink and the red vector both go to the same spot. So even if I were going to undo that, which one do I pick? It turns out one way of answering this question is by looking at areas. Here I have a bunch of regions between vectors on the left. I've got the corresponding region on the right. Notice that in all of those cases, the areas have gone up by a factor of 5. That's why we might want to associate the number 5 to this matrix. There's nothing special about the regions I drew. This would work for any shape. If we study how it transforms, this matrix is going to multiply the areas by a factor of 5, and we call that the determinant. In general, we use this formula here, and it's possible that we could get negative values. In that case, ignore the negative sign when thinking about area, but I do want to show you what that negative sign means. Here's a relatively simple matrix. It takes the blue and gold vectors over here, but notice it turns things upside down. We've switched the orientation. We still get a factor of 2, but that explains why there's a minus sign in the determinant. Anytime there's a collapse, our determinant is going to be 0. That's because we have no area on the right. It's not even the right dimension. And that's why a square matrix is invertible if and only if the determinant is non-zero. Maybe now you know that this is really about area.